All right, so in assignment number 5, we're talking about rational functions and their graphs. And so rational functions come about in a situation like this. Sarah was 3 out of 16 in her first basketball game. 3 out of 16 is not a very good percentage. So to be recruited by Division I colleges, her coach told her she really needed to have a shooting percentage of 40%. So if she doesn't miss in her next game, like if she makes her next shot in the next game, she's going to be 4 out of 17. And if she makes the next one, she's going to be 5 out of 18. All of these increase her percentages. But if we continue with this idea, she's going to end up making X number of shots out of X number of shots. And she already made 3 out of 16. And so we would set up a specific equation to solve this example that would look something like this. She had 3 plus, she's going to make X in a row. She's already shot 16, and she's going to take X in a row. And these numbers are the same if she keeps making every one that she takes. We would want to know when is that equal to 40%. So that's a rational function. Today we're not really going to work on solving these rational functions. We're going to work on graphing those rational functions. A rational function is simply a function with an entire function on top and an entire function on the bottom. And we have that here because one function is x plus 3, that's the one in the numerator, and then the other function is x plus 16, which is the one in the denominator. So we have 3 examples that we're going to go through and just kind of talk about several things in these graphs. And so if I take a look at this graph, I can make an x and y chart for what's going on. If I just simply did something like this and I plugged in 0 for x, I would have 0 squared on top, which is 0, and then 0 squared on the bottom plus 1, which is 1. And so that's going to give me 0. And so I'd have a point at 0, 0. I could do this with other numbers too. Like if I plug in 1, I'd have 1 on top over 1 squared, which is 1 plus 2. That's going to be a half. If I plug in -1, it's also going to be a half. If I plug in 2, then it's going to be 2 squared or 4 on top over 2 squared plus 1, which is 5 on the bottom. That's 0.8. Well, if you graph this on something like Desmos, you get a graph that looks something like this. Here's the point at 0, 0. We have the point at 1.5. We have the point at 2 and 0.8 and so on. If we plug in negative numbers, we get the same thing. But what's interesting is that we have an asymptote here. The reason we know that that's an asymptote is because it's never going to reach 1. Even if I plug in, let's say 10, if I plug in 10, 10 squared is going to be 100 on top. And on the bottom, I'm going to have 10 squared, which is 100 plus 1. So 101 on the bottom. Well, that's going to be close to 1, but not quite 1. It's never going to reach 1 if I go to the right or if I go to the left. And so that's a horizontal asymptote. So here are some of the things that I'm going to want you to figure out. The first thing that I'm going to want you to figure out is what the domain looks like. And you can see that the domain, it goes forever to the right and forever to the left. And so the domain is simply going to be from negative infinity to positive infinity. The range, now the range is different in this case because it only goes from 0 to positive 1. Okay, we can't get anything else besides those numbers. And there is a horizontal asymptote here at 1. But we could find that horizontal asymptote before we plugged any numbers in. We could just look at the leading coefficients, or the leading terms and their coefficients. So for example, if I look at the leading coefficient here, it's 1. The leading coefficient here is 1. That simplifies to 1 over 1. Which is 1, which means my horizontal asymptote is going to be at x equals 1. The reason for that is if I plug in a huge number like infinity, I'm going to have 1 infinity squared here and 1 infinity squared here plus 1. And so it's not like this is going to make that much of a difference, the plus 1. It's going to be really, really close to just 1. If I had something like this where this had a coefficient of 2 and this had a coefficient of 1, well, then my asymptote would not be at 1, it would be up here at 2, because I would have 2 infinities over 1 infinity, which is always going to, as x gets closer and closer to infinity, it's going to approach 2. So the question then is this: how does the leading term allow you to find the horizontal asymptotes? Well, we divide or we simplify the coefficients of the leading terms. And so you can put down here, I'm not going to spell it out, it'd be really sloppy anyway, but you take the coefficients of the leading terms and simplify this. If this were to be something like this, let's say it was y equals 1x over 3x. Well, the leading term is x, so it would be y equals 1/3. And there would be an asymptote about here at y equals 1/3, a horizontal asymptote. And so that's how we find horizontal asymptotes. And this is continuous because I don't have to pick up my pencil at all to draw this graph. My marker just stays on the screen the whole time, and I can cover the entire graph. So that's a continuous function. Then we get to functions that are discontinuous. And this is an example of a function that's discontinuous. In other words, I'm going to have to pick up my pencil to draw part of the graph. It's kind of misleading because if we cancel these x plus 2's out, it looks like this is going to be the same thing as y equals, boy, that's sloppy, y equals x plus 3. I have a pen here that's not really working that much. Let me just use my fingers. X plus 3. And if you punch this into Desmos graphing calculator, you get something like this. We have the slope here is 1, and we have the y-intercept of 3, and that's exactly what's going on over here. We have a y-intercept of 3, and the slope is 1, so we get this function. But what you don't see is that there is a hole in this graph, and that is where x is equal to -2. X cannot equal -2. And the reason it can't equal -2 is because we're going to have a 0 in the denominator. If I take -2 and I plug it in for x, that's going to be -2 plus 2, which is just 0. And so I would have 0 over 0 here, which is undefined. And so there's actually a hole in the graph right here at -2. In other words, I could sketch this graph by sketching this part, but I'd have to pick up my pencil to go from the first part to this part of the graph, because there is a hole there. Now, it's such a small hole that you can't see it when you graph it on Desmos or if you use your graphing calculator, but there is a hole in the graph, which means when we're finding the domain, we would say that the domain would go from -infinity to -2, and then it would go from -2 to infinity. Okay, I had to pick up my pencil somewhere along the way to graph that equation with a hole in it. Now what's interesting is the range is also going to be discontinuous. The range is the y values. I can never get a y value of 1 because that's where the hole exists. And so it'd be nice, it looks like with this equation I could get 1, but in order to get 1 I'd have to let x equal -2 because -2 plus 3 is 1. But -2 can't work because I can't have a -2 in this function. It gives me something that's undefined, which means the range here is going to go from -infinity to 1, and then from 1 to infinity. So how do we tell where the hole is? Well, first of all, the hole is going to be where x is equal to -2. Okay, because we could say, specifically we can say it's at the point -2, 1. Okay, but this is good enough. We can say x is equal to -2, and there's going to be a hole at the graph. And the reason we know that is because anytime we have a factor that cancels out, there's going to be a hole, and if there's a 0 in the factor, that's where a hole will exist. And so because we have something like this where we have x plus 2 over x plus 2, we know because of this over this, we know there's going to be a hole at -2. And so here's a question that we should be able to answer. How can you look at a function and find the hole? Well, anytime you have a factor on top and a factor on the bottom that could be equal to 0 somewhere, and it cancels out, there's going to be a hole at that spot. That's called a point of removable discontinuity. Okay? And there's the hole. Here's another situation, example number 3. Okay, so it's a few things going on here, but there's nothing that's going to cancel out. I don't have an x minus 2 on top that's going to cancel out the x minus 2 on the bottom. But at the same time, we know that x cannot equal 2, because if it's equal to 2, then we have a 0 in the denominator. Well, if we get a 0 in the denominator, but it doesn't cancel out, well then we don't have what's called a hole in the graph, we have a vertical asymptote. And so, for example, you can see if I graph this on Desmos graphing calculator, I have a vertical asymptote right here at 2. Okay, and the reason for that is because x cannot be 2. Okay, so I'm not going to get anything if I plug in an x value of 2, and it's not a hole in the graph because it doesn't cancel out. Here's another thing that we know. We know by looking at this that the leading terms are 1x over 1x, which means there's going to be a horizontal asymptote at 1. And you can see that right here. There's a horizontal asymptote at x equals 1. And we have a vertical asymptote at x equals 2. The horizontal asymptote is at y equals 1. And so let's just take a look at some of the things that we want to figure out here. First of all, the domain. The domain is going to be all the x values. The x values are going to go from negative infinity to 2, and then from 2 to positive infinity. There's going to be a break at 2. And then the range of the y values, that's going to go from negative infinity to 1, and then from 1 to positive infinity, because there's a break here at this horizontal asymptote. So where is the horizontal asymptote at the graph? The horizontal asymptote is at y equals 1. Where's the vertical asymptote on the graph? The vertical asymptote is at x equals 2. And this is where there's an asymptote, it's called a point of non-removable discontinuity, because it's not like I'm just pulling out a point on the graph. It's an entire asymptote. And so that's how we find the horizontal or the vertical asymptotes. All right, so what about these three graphs? Well, certain things that we can find out about them. First of all, we want to talk about the domain and range, which we've been doing. We want to figure out what the x and the y intercepts are. Now, this is something that you should know coming into this. You can find the x-intercept by letting y be 0, and you can find the y-intercept by letting x be 0. So, for example, we can find the y-intercept here by letting x be 0, which means it's going to be negative 1 over 16. If I graph this, I'd put this into Desmos, and negative 1 over 16, this looks like it crosses at 0, but it really crosses the y-intercept at negative 1 over 16. Here's some other interesting things. The x squared here isn't there because it's like a 0x squared over a 1x squared. Well, 0 over 1, that's 0. That means there's a horizontal asymptote at 0. There's also a vertical asymptote. X squared minus 4, that can be factored, or x squared minus 16 can be factored to x plus 4 and x minus 4. That means there's a horizontal or a vertical asymptote at negative 4, which is here, and positive 4, which is here. If we look at number 5, if I factor the top, is going to be x plus 1 times x minus 1. So here the x plus 1's cancel. There's going to be a hole in this graph. Okay? It's going to look like y equals x minus 1, which the slope is 1 and the y-intercept is negative 1, and it looks like this. Except there's going to be a hole at x equals negative 1 right here. You can't see it on the graph, but that's where the hole exists, because we know that x cannot equal negative 1. We can find the x and the y-intercepts by letting the other one be 0. There aren't any asymptotes in this situation because there's just a hole where the denominator is equal to 0. And then finally, if we take a look at number 16, let's see if this factors down here at all. We're going to have x times x gives me x squared, and then a plus 2 and a plus 1. So these will cancel. There's going to be a hole at negative 1. So at negative 1, there's going to be a hole, which is going to be about right there. That's where x is negative 1. There's going to be a vertical asymptote at x equals negative 2, and you can see that. That's right here. If we look at the leading terms, the leading term here would be 1x squared, but I have 0x squared on the top. It's not even listed. So 0 over 1, there's going to be a horizontal asymptote at 0. So there's more that we can tell about these graphs, but we should be able to find vertical and horizontal asymptotes. We should be able to find holes in the graph, the x and the y intercepts, and the domain and range. And that's what you'll be working on your homework assignment, which is assignment number 5 in Math Excel. And if you have questions, we'll go over it tomorrow in class.